take a look today at arc length along a curve. So we're going to use the distance between 2 points to develop the formula first, and then we're going to use the formula to write and evaluate integral expressions to find that particular length. So what we're looking at is a curve like this, and basically wanting the distance between this point and this point. Okay. Okay, and if I wanted the distance between those two, I could find it with the distance formula. But that straight line is not that accurate for the distance along that curve. I could try instead saying, let's find two different ones. Let's add another point in between. And let's do from here to here, the point in between, and then that one. That looks a little bit better, okay? But do you agree we're still not perfect? Okay. So then what if I do 4 points? Oops. Come on. I'll do like one there, there. So now if I'm going to do 4 points, I'd have like that distance, and that distance, and that distance, and that distance. And you can see at 4 points was significantly better. And the idea here is that as I do more and more points, I'm going to be a better approximation for that curve until the limit, as we approach infinity, okay, doing an infinite number of points would actually be the curve. So basically, I'm looking for the limit as n approaches infinity of the sum of all of these distances. Well, in that case, I'm going to use the distance formula, which is the square root of xi minus xi minus 1 squared plus that, with change in y's, okay, which is really the change in x squared plus the change in y squared, okay, the square root of that. So change in y squared, here's where it gets a little weird. That's really f prime of x1. So the slope, the change, it's really the steepness of the curve at that particular point times the total change distance, which ends up like that if you distribute the squared into both of those pieces. And then you end up with that messy looking thing. Okay, so you have 1 plus f prime of xi squared times the square root of the change in x squared. Okay, well, that change in x squared, is like having a change in x on the outside. Okay, well, that we know that change of x, that's just dx. So you end up with this arc length formula. The length of an arc of function y equals f of x from x is a to x is b is given by this formula. From a to b, the square root of 1 plus the derivative quantity squared dx. In alternate notation, we can have it look like that with a dy dx on the inside instead. Take a preference. So I'm walking along a path defined by y equals ln of secant x from x is 0 to x is pi over 4 miles. At the end of my stroll, how far have I traveled? Give an exact and approximate answer. And yes, I only travel along paths that can be mathematically expressed. Haha, so funny. So first thing I'm going to do is find the derivative. Okay. So I have y equals ln of secant x. So when I find y prime, it's going to be 1 over secant x times the derivative of secant because of the chain rule, which is secant x tangent x. I end up with y prime is secant x tangent x over secant x. Tell that those secant x are going to cancel, and so the derivative is tangent x. Okay. So what I'm going to do now, I want to know what the derivative squared is. Well, that'll be just tangent squared x. So when I find that arc the integral from 0 to pi over 4, because that's where it was saying those bounds were, the square root of 1 plus tangent squared x dx. Well, 1 plus tangent squared, that's the same as secant squared by those Pythagorean identities. So now I have the square root of secant squared. Square root of secant squared will be just secant. Derivative, sorry, not the derivative, the integral of secant x, that is one we had to memorize. Hopefully you still have that memorized. It's ln of secant x plus tangent x. And then I want to evaluate that at pi over 4 and 0. So, and it's absolute value because we don't want to have negative in there by any problem. Tangent, ln of a negative is not a good thing. So, and I just am evaluating. So, we end up with ln of the absolute value of the square root of 2 plus 1 minus ln of 1 plus 0. So, I can lose the absolute value bars now because 1 plus the square root of 2 is not going to be negative. And then I have ln of 1, and ln of 1 is 0. So my answer is that. If I wanted a decimal approximation, I'm going to use my calculator, and we will get about 0.8813. So take a minute, pause the video, and try this problem, please. Right, so hopefully you've tried this one. We're going to start again with the derivative that y prime is equal to 2 root 2 x to the 1/2. Then when we square that, we'll get 8x. So now what we'll do is we'll do the integral. Our arc length is equal to the integral from 0 to 1, the square root of 1 plus 8x dx. Unlike the last one, we don't have any fancy tricks that's going to get rid of that square root for us. So what we'll do instead is a u substitution. So I will make my u 1 plus 8x. That means du is equal to 8 dx. From there, 1/8 du to dx. So when I adjust my integral, I'm going to adjust my bounds of integration. So 1 plus 0 is 1, and 1 plus 8 is 9. 1/8 in the front from that coefficient, and then I'll have u to the 1/2. So we'll have 1/8 times u to the 3/2, 2/3 in front, and then we want to evaluate that 9 and 1. So 1/12, 9 to the 3/2 minus 1/12. 1 to the 3/2, but that's just 1. And that comes out as 13/6. So one thing to always keep in mind on these, because we're relying on the derivative of a function as part of the integrand, anytime the derivative of a function fails to exist in the interval of integration, because of it being a vertical tangent or cosp, discontinuity, anything like that, we just need to be very careful. We can also write it in terms of y. Usually we just write c to d instead of a to b because we want to make sure that these bounds of integration are based off of our y values, not our x values, and we're doing g prime of y. So this derivative is dx dy instead of dy dx. Sometimes that is helpful if I had like x equals y cubed plus y, something that would be hard to work with in terms of x. If I wanted the arc length of a function, I'm just going to do the integral, but my final value for my bound, my upper bound here is going to be a variable instead. One thing to notice here in this formula, I have t's in my integral and an x up in there because by the fundamental theorem of Calculus Part 1, find the arc length function for the curve y equals x squared minus 1/8 ln x, taking p 1, 1 as a starting point. So we're going to have L of x is equal to from 1 to x, and then I'm going to have the integral of 1 minus, I want the derivative here, to t, make sure you have that in terms of t in the inside, 1 over 8t squared. Oops, plus sign right there. Let's fix that. All right, so now I'm going to FOIL on the inside. I'm going to get 4t squared minus 1/2 plus 1 over 64t squared t. So now I have the integral from 1 to x. Combine my like terms, 4t squared plus 1/2 plus 1 over 64t squared dt. Next step, I'm going to actually factor that. It should feel really familiar because it's basically what we just FOILed, but instead it's going to have a plus sign in it. That's convenient, especially because that's squared now and the square root are going to cancel each other out. Fantastic, right? dt. Now I'm going to do the integral. I'll have t squared plus 1/8 ln t. I want to evaluate that at x at 1. And so L, did I use L of x or did I use S of x? L for length. You could also use S of x, not wrong. X squared plus 1/8 ln x minus 1 squared minus 1/8 ln 1. Ln of 1 is 0, so this is really just x squared plus 1/8 ln x minus 1. Like this. And this concludes our lesson on arc length.